Hi, in this video, we want to take a look at model selection and model validation in multiple linear regression. Okay, so our goal for this is that after I've built a model, I want to see, is it a good model? If I build multiple models, I want to go, hey, which one's the best? Now, before we even get to that point, we're going to talk about model selection. And so for model selection, I'm going to specifically talk about three particular ways that we can automate the process of deciding if a variable, a predictor variable, should be in our linear regression model. And this will do a lot of the work for us. All right, so let's dig into it. Linear regression is a simple yet powerful technique for modeling relationships between a target variable and predictor variables. When there are multiple predictors, the model selection process can be rather difficult to wade through. So additionally, after fitting the model, it is essential to validate the model and ensure that we have like a good model, but that we want to actually launch. All right, so let's talk about model selection. So for model selection, since we're only focused on multiple linear regression and only one type of model structure, when I say model selection, that really for this purpose is actually which predictor variables are we going to include. All right, so if this is the general form of our model, so we have our target variable, we have our intercept, we have predictor variables, we have coefficients for the predictor variables, and then we have an epsilon, and this accounts for all aspects of what's going on with our target variable that's not accounted for with our predictor variables. So y is our dependent target variable. Each x is a predictor variable, an independent variable. The betas are parameters. Beta 0 is the intercept, and the rest are coefficients of our predictor variables. And then epsilon is our error term. So when there are a whole bunch of predictors, we might not want to include all of them. So imagine the situation where I have 2,000 predictor variables. This is a realistic situation to be in with modern data. All right, so if I just dump all 2,000 in there, there's a high chance that I'm going to overfit, have multicollinearity, and difficulties interpreting my model. So I don't want everything in there. So we need some way to go through and decide which predictor variables to include, which ones to exclude. Now, if I have thousands of predictor variables, I can't use subject matter expert to really wade through all of them. Now, subject matter expert is the best way to go through to use knowledge and understanding of what's going on, but it's common that you're going to, the database that you're pulling your data from, or maybe the study that you're working on, you don't have previous experience with what you're talking about, with what you're working with. And what we're going to do, we're going to come up with 3 different algorithms for going through and selecting which variables should be in there. We've got 3 methods: forward selection, backward elimination, and stepwise selection. Forward selection starts with only the intercept as a model, and then checks to see should we add one variable, and finds that one variable to add. Tack it on there. Now, forward selection goes, hey, should we add a second variable? Looks through, and if we should, adds it on there. And then keeps on repeating this process until a stopping criteria is met. Now, backwards elimination goes the opposite direction. So forward selection started with basically nothing and added to it. Backwards elimination includes all variables in there and starts removing predictor variables. So what it's going to do, backwards elimination, takes all the predictor variables and then checks to see, hey, could we get rid of one of these? If we should, get rid of it. Now, you have a not quite so big model. Check to see, should we get rid of any of these variables? If we should, get rid of it. Repeat until some stopping criteria is met. Now, stepwise selection, this is a mixture of the two. This is forward, then back. Forward selection of adding variables to a simple model, and then after you add, double check to make sure that you've got the actual model you want. And that's the forward back stepwise selection process. And so that's a way for us to automate the selection of predictor variables. Now, of course, if it's feasible for us as humans, we want to actually make sure that we have like a short list of predictor variables that we should use. We want to make sure that we have quality data. We want to make sure that from our understanding of the situation, the variables that we even start out with are useful. If I have a whole bunch of just crap variables and I throw them in, the algorithm likely is going to grab some crap variables and just keep them in there just because of the sheer volume of them. So it's very important that when I start out, I start with good quality data going in, even if I'm going to invoke these techniques. Now, model validation, this is more recent to data science than the other techniques that we're going to talk about. Model validation is really more of a machine learning point of view. And here we want to check the accuracy of our data. And so what we're going to do is I'm going to check to see how accurate my model is under certain conditions. And which one I will use will depend on the situation I'm in, the size of data that I have, and what my stakeholders are comfortable with or what I'm comfortable with. So I'm going to go over 3 different methods. First one is the holdout method, then the cross-validation method, and then bootstrap. All right, so for the holdout method, what we're going to do is I'm going to take a fraction of my data. Let's say maybe 3/4 of my data, 75% of my data. I'm going to make that my training data. I'm going to build my model on this. Now that remaining 25% was not in the training process, was not used to build my model. That last 25%, what I'm going to do is after I have my model, I'm going to apply my model to that held out 25%, and I'm going to check the accuracy there. And so what this does is gives me a better estimate of performance than if I would have used the residuals. Because so something that's going to happen is that when you run a statistical model, a machine learning model, it's going to tune to the data that you have. And so your residuals from training your data, your training data set, your residuals will always be optimistic unless you have like outliers going in there. Assuming you don't have outliers or anything really weird going on, your residuals from your training data set will be smaller than they will be going forward in real life. Now, cross-validation, how we handle this is that I'm going to break up my data into subsets. And then I'm going to, for each subset, I'm going to hold it out like I did previously in the previous holdout method. But I hold that out, and then the rest of the data, I'm going to build the model. Now, what's different with cross-validation is I'm going to break up my data. Let's say, just to keep it simple for explanation, I'm going to break up my data into 3 parts. I have approximately 1/3 each. I'm going to take the first holdout set. I'm going to use the other 2 to build the model, and then I check accuracy with the model I get. Then I'm going to take the other, let's say the second holdout set. I take the second holdout set, hold it out. Then the first and third I use to build my model, and I check accuracy on that second holdout set. Now, last but not least, I grab the third holdout set from cross-validation. I take the first and second, build my model, check accuracy on the third holdout set. And so that's cross-validation. This is the one that I prefer to use. Today at work, I use the holdout method and cross-validation both for different projects. Now, the next one is Bootstrap. All right, so for Bootstrap, what we're going to do is I'm going to sample my data with replacement. So let's say I have 100 data points. I'm going to sample with replacement. That's important. With replacement, you keep on hearing me say that. With replacement, 100 data points, 100 rows of data. So with replacement means that some of them are going to be resampled in there. Well, if I take 100 data points, I have 100 to pick from, and some of them get repeated, then some of them are left out. And so I'm going to sample with replacement, equal number of rows as I have in my data. I'm going to build my model. Now, all the data that did not get sampled, that was not part of building the model, I'm going to use that as my holdout set for checking my the accuracy of my model. Frequently, we will do this over and over and over. Why do we like this? Because this gives us a way of of getting like a distribution of value of a statistic that tells us information about our model. So if I wanted to, I could look at, let's say, R squared. I could do bootstrap R squared, then compute R squared multiple times, and I'll have a distribution of the R squared values. And so that gives me more information than I would get from just one run. Statisticians love this. Now, Bootstrap is typically done with smaller data, and that's a huge advantage to this over the other techniques. Holdout and cross-validation are typically used when we have more data to work with. All right, so there are several ways that we can check validation. We mean squared error. So this is the one that classically trained statisticians like the most, because mean squared error connects directly to some aspects of hypothesis testing and linear regression. There's root mean squared error. The reason we like this is that when I square the error, then like let's say my unit of measurement is in feet, and then I square it, then I'm going to have feet squared. That means my mean squared error is going to be in feet squared. Well, we like things to be on the same unit as measurement. So if I had feet as my unit in the beginning, root mean squared error will give me feet back, while mean squared error will give me a measurement in feet squared. Now, mean absolute error, this is one I use today for work. This is observed minus the modeled value, take the absolute value, and then take the average of those absolute values. Add them up, divide by number of observations. That is the mean absolute error. I like this one the most for talking to my clients because I can say this is the average error. For theoretical work, I prefer mean squared error. Now, R squared is a way for us just to check the correlation between our model values and the values that we see in our data. So model selection and validation are essential steps in the process of building a reliable linear regression model. They allow us to avoid overfitting and ensure that the model's predictive performance and ability to maintain, or ability to model what's going on, can be actually interpreted. So let's talk about ways to measure model quality. Okay, so here, when I talk about model quality, this is always a relative thing. So if I have one model and I run these statistics, it really doesn't tell me anything. One model, one value by itself isn't informative. But these ones I'm talking about here that you see on the screen, these are useful when I have the same data set and I want to compare different models to see which one is the best one to use. Okay, so imagine I did that forward selection, backwards elimination, and I did stepwise selection. And let's say I have an intercept model and I have the full model with all the data just dropped into it. There I have 5 models to work with. I want to know which of these 5 is the best. Well, here we're going to use the model quality criteria that we're going to talk about to evaluate which one is the best. And so remember that it has to be the same data that I'm building the model on for me to be able to compare things. All right, so the ones I want to talk about are Akai's information criterion. This is coming from information theory, Bayesian information criterion, corrected AIC, and Maslow's CP. All right, so Akai's information criterion. This is based on information theory and considers both the statistical goodness of fit and the number of parameters used to achieve the model. All right, so what we're doing here is that I'm going to consider goodness of fit as like that's good. I want high goodness of fit, but a parameter, higher parameters is bad. So what we want to do, we want to simultaneously consider how well does it fit, but how complicated of a model do I have? The more parameters I have, the more complicated the model is. Okay, so what we're doing here is that it works out that if I was if I had, let's say, 5 predictor variables, and I took any random variable I could possibly get, take a random numbers in there and threw it in there, then it is guaranteed mathematically that the fit of my model from a sum of squares error point of view, my sum of squares error can only go down if I keep on adding variables. Well, if I keep on adding crap variables that aren't informative, sum of squares error makes it look like I have a good model, but in reality, I don't. And so we need to balance goodness of fit with complexity of the model. And how are we going to do that? We're going to take 2 times the number of parameters minus 2 times natural log of the likelihood. All right, and so the likelihood comes from assumed distribution of what's going on. And so here, this is a penalty for being more complicated, but this counteracts the penalty when I have a really good fitting model. So we're trying to balance this out. Now, something about this is that some packages, such as BNLearn, will actually reverse the sign. They'll multiply by -1 on this. And so check your help documentation before you start using AIC. In general, lower AIC is better. Also, AIC can only be used to compare models on the same data set. That's important. So if I have 2 different data sets and I check AIC on both of them, they're not comparable to each other. It's an apples and oranges point of view. Now, the Bayesian information criterion is very similar to AIC, except there's a stiffer penalty. So here you'll notice that we have a 2. Down here we have a natural log on the number of observations. So it's otherwise, this is the same formula. So once again, we're trying to balance goodness of fit with complexity of the model, and lower is better in this presentation. Check your help documentation. So by having a larger penalty aspect, you see that this coefficient is bigger than 2 for virtually all cases. What we're saying is I really value a simple model. So I'm willing to sacrifice goodness of fit to make sure that my model is simpler when I'm working with BIC. Now, in the mass package, I can choose any coefficient here I want. I personally prefer AIC. I've had the experience of BIC being a little bit too rigorous on pushing out variables, but it's up to you, up to your stakeholders. The most important thing is that you check model quality. How you check model quality is nowhere near as important as you do it some way, some shape, some form. Do it the way that your stakeholders, your boss, will be most receptive to. Now, corrected AIC, what this does, this adds a correction term to AIC to give an adjustment for small sample size. If I have a large sample, then this correction is so small that we don't even need to worry about it, honestly. It'll be negligible. So we don't worry about it. When I have a small sample size, that's when corrected AIC is more important. Now, Maslow's CP, this criterion is used specifically in the context of regression and is a tool for comparing different regression models. It's especially useful when conducting stepwise selection and other similar methods of model selection. Here's the formula. So you see I've got sum of squares error divided by the estimated variance minus sample size plus 2 times the number of parameters. A good model will have a CP close to the number of predictors in the model plus some constant. These are all methods for ensuring that the model fits the data well without overfitting or incorporating too many parameters. In general, when comparing models, those with lower information criteria values are preferred. All right, so now let's go ahead and dig a little bit deeper into the stepwise regression methods. So remember, we've got forward selection, backwards elimination, and stepwise selection. Forward selection begins with an empty model, so just the intercept, and adds predictors one by one. In each step, the predictor that gives the highest improvement to the model is chosen to be added. This improvement is typically measured by a drop in the residual sum of squares or an increased R-squared value. Mathematically, given P predictors at the first step, we fit P simple linear regression models and choose the simple linear regression model that gives the lowest sum of squares error, or the highest R squared. In the next step, we check to see among the P-1 remaining predictors, which one added on would improve our model the most. And we repeat this over and over and over. The procedure continues until some stopping rule is met, such as no variables remaining, or a predetermined number of predictors has been included. In the mass package, the stopping point is when the AIC or the BIC no longer improves, because that considers model complexity and goodness of fit simultaneously. Advantages of forward selection: it's computationally efficient, and we can use it for large data. It's simple and intuitive to work with. Disadvantages: all right, so it might include a variable earlier on that will be redundant as other variables get added onto it, and it doesn't consider removing a predictor once it's added. So in this process, once it's added, it stays in the process. Now, backwards elimination, here we start with a full model, every single predictor, and we start kicking them out until we have a model that we like. Backwards elimination is the opposite of forward selection. It starts with all predictors in the model and kicks predictors out one by one. In each step, the predictor that causes the smallest degradation of the model is removed. Mathematically, given a model with all P predictors, we remove one predictor at a time and monitor the change in sum of squares error or R squared, or whatever statistic you want to use. For me, when I learned this initially, the professor talked about sum of squares error and R squared value. The variable whose removal produces the smallest degradation is removed, and the process is repeated until a stopping criteria is met. Advantages of backwards elimination: it considers the global structure of the data as it begins with the full model. It's relatively simple and intuitive. Disadvantages: all right, so this is not applicable when the number of samples is less than the number of predictors. So if I have fewer rows of data than I have columns of predictor variables, I can't use this. Linear regression can't handle that situation. This can also be computationally expensive, especially when we have a large number of predictor variables. And also, it doesn't consider removing any predictor variables once it's in there. Now, stepwise selection, so this is a combination of forward and back. We do forward selection, backwards elimination, over and over and over. So we start with an empty model and we add a predictor one by one, as in forward selection. However, after each time we add a variable to the model, we check if all the variables in the model are worth keeping and remove any that should be kicked out. Advantages of this is that it balances forward selection and backwards elimination. It's more accurate as it considers both adding and removing predictor variables. Disadvantages: this is computationally expensive. It also leads to a lot of comparisons. And so from a hypothesis testing point of view, if I'm doing a lot of comparisons, it's harder for us to not have made a mistake along the way. A lot of comparisons means more opportunities to make a mistake. Stepwise selection has a lot of comparisons. Each method has its own strengths and weaknesses, and the choice depends on really what's important for my project. It's also worth noting that these are like algorithmic methods that do not guarantee to find the best method, the best model. There are other techniques for fitting a regression model, like lasso, ridge, and elastic net, which perform variable selection and regularization. And these are popular, but these are really more of a machine learning topic. So I'm not going to present it here because our focus is statistics, where we want to be able to do hypothesis testing. And in linear regression, we can do tons and tons of hypothesis testing. All right, so now let's take a second look at model validation. Let's talk about the holdout method. The holdout method involves splitting the data into a training set and a test set. The model is fitted on the training set and evaluated on the test set. A typical split is 70-30. 70 for training, 30 for testing. And this method is easy to implement and computationally efficient. However, its performance can vary a lot depending on how things are split. So this has a good amount of variability. Advantages to the holdout method is it's simple and easy to implement. It's computationally efficient because we run things pretty quick. Disadvantages is that it can lead to high variance if the data is split differently, meaning model performance can significantly change depending on the train test split. This is particularly true if I have not dealt with outliers. If I haven't dealt with outliers, then when that outlier is in the training set, it can throw off my model. And when it's in the test set, I can get a worse test statistic than I should have. The model doesn't get to train on all portions of the data, which can be problematic when the data set is small. Now, the next one is cross-validation. Cross-validation is similar to that holdout method that we talked about a moment ago, but it repeats it multiple times with different partitions of the data. So I'm going to partition my data into subsets, and we call this k-folds. And so we'll say k-fold cross-validation. K is the number of subsets I partition my data into. And so each time we're going to train our model on k-1 subsets, and we're going to test on that hold out data set for that. And then whatever statistic I want to use, I'm going to take the average of the k-1s to get my estimates. Advantages of cross-validation: it provides a more accurate estimate of out-of-sample error. It makes efficient use of the data since the data is used as training and test. It also has lower variance than holdout method due to this averaging aspect. Disadvantage: this can be computationally expensive, especially if the data set is large or if the model is very complicated. Usually with linear regression, it's not complicated. Now, Bootstrap. So remember, in this case, I'm going to sample my data with replacement. So I resample my data. Then I'm going to fit my model on the resample, and I'm going to evaluate my model on the data that's not in that resample. And we can do this over and over and over. This is especially useful for small data sets. So advantages is that this gives us a robust performance estimates. If I do this over and over and over, I can get distribution of the value that I'm interested in, the statistic. And this is especially good for small data sets. And we can use it to estimate uncertainty around performance metrics by getting a distribution of them. Disadvantages is that this can be computationally expensive due to the need to fit models multiple times. It assumes the data is independent and identically distributed, which might not be the case in a time series or spatial data model. Now, this next one is leave one out cross-validation. This is a special case of k-fold cross-validation where k equals the number of observations. What we're going to do is for each individual data point, I pick out that data point, I build my model on the rest of my data. Then I take another data point, pull it out, build my model on the rest of the data. Find one data. So I'm going to end up building in models for this. And this is leave one out cross-validation. So I'm pulling one data point out each time. And then when I build the next model, I put it back in, pull out a different one. All right. And so then we take an average for our cross-validation. Now, advantage is it makes maximum use of the data as each observation is used in training n-1 times and for testing once. It has low bias as each test set is almost the same as the original data set. A special formula for linear regression makes it super fast to compute that only applies to linear regression. So if I'm doing a linear regression problem, we have a special formula that works out leave one out cross-validation for us. Disadvantages: if we're not doing linear regression, this can be computationally expensive, especially for large data sets or for nonlinear regression models, complicated models. And it can have a high variance off of it, from just pulling out values. And so in summary, the choice of model validation depends on the trade-off between bias and variance and computational resources. The holdout method is simple and computationally efficient, but suffers from high variance. Cross-validation and leave one out cross-validation reduces bias by using more data for training, but can be computationally expensive. And the bootstrap method, this is the only one that we'll talk about here that can handle small data sets. This can provide robust estimates of performance, but this can be computationally expensive because I have to do it over and over and over. All right, so here we want to take a look at model quality using R. So here's my baseline model. I'm taking the MT-CARS package. I'm going to say miles per gallon depends on cylinders, horsepower, and weight. And here is my model. Now my AIC for this is 155. My BIC is 162. And BIC, for large enough data sets, BIC will always be larger than AIC. But remember, I don't compare AIC to BIC. I compare AIC to different models on the same data set. I compare BIC to different models on the same data set. Now, for corrected AIC and Maslow's CP, base R doesn't have a function for this. I'm sure there's a package that will do it, but it's simple enough to just compute. Also, AIC, corrected AIC, BIC all have varying formulas. And so here I just wanted to be consistent with the formula above. So here's my corrected AIC. And then for Maslow's CP, I'm just going to do a little bit of extra computation and we'll get it. And so Maslow's CP for this particular model is 2. Now, let's take a look at stepwise regression using R. All right, so what I'm going to do is I'm going to start with an empty model, and I'm going to start with a full model. Notice I have a dot here. When I have a dot in the formula in R that says use everything. All right, so here I have only the intercept, no predictor variables. I have all predictor variables from the MT-CARS data set. Now, in the mass package, we have step AIC is by far the most common way to implement stepwise selection in R. So we're going to take our model intercept and we're going to look at doing forward selection. And our scope, this is how we can limit our model. Say, I can say I want this one to be the simplest model possible, or lower, I can say that I want this one to be the most complicated model. And so by controlling the scope, I can say I only want models in considering this range of possible variables. All right, so what has happened here, we start with the intercept model, and each one of these predictor variables was considered on their own in simple linear regression, and it was sorted by the AIC. Smallest AIC is weight, so we're going to add weight to our model. Boom, now we have the intercept and weight in our model. Now we're going to consider adding another variable. All right, we have cylinders, horsepower, Q-sec, and keep on going. And we see that cylinders has the lowest AIC after adding it to the model. So we're going to add cylinders to the model. Boom, I've got that. Now we're going to go and we're going to consider adding another variable. And it looks like horsepower would result, if I add it, would result in the smallest AIC. So let's go ahead and add horsepower to our model. Boom, we've got it. And now when I check the AIC here, I see that I would not actually get an improvement by adding another variable. So if I add another variable, the AIC will increase for all of the variables. So I'm not going to add any. I'm done. I stop. Good. I've got my final model. Now, as I look at the summary of my model, you'll notice, hey, horsepower is not statistically significant. Huh. All right, so what's going on here is that statistical significance and AIC really are different measurements. They're both, driving towards like model quality and should this be in the model, yes or no, but they're different measurements. And so it's kind of like if I want to measure athleticism, I could do a bench press and have people do bench press and see who's strongest to measure athleticism. I could also have people run marathons and or have them run a sprint and measure athleticism that way. Different measurements will result in different models being optimal. All right, so now let's do backwards elimination. We're going to start with the full model. And now here in this part, you'll notice I've got negative signs instead of plus signs. So we're considering removing these variables here. And we can see that we get the best improvement if I get rid of cylinders. So cylinders, you're out. So now this is my new model. So now I'm going to check to see which variable being removed would give the best improvement, VS. So let's go ahead and remove VS from the model. You notice it's not here, so this is my new model. And I'm going to keep on doing this. Remove carb. Here's my new model. Remove gear. Here's my new model. Remove drat. Here's my new model. Remove displacement. Here's my new model. Remove horsepower. And now I won't improve my model if I remove a variable. Whoa, okay, so now I've got my final model. And you'll go, well, wait a second. That's different than the backwards elimination model is different than my forward selection. All right, so different methods will result in different models. And now here we see that all my variables are statistically significant. So, we might want to consider using this one. It depends on what's important to you, which statistic to go off of. Now we want to do stepwise selection. I'm going to start with the empty model with just the intercept. Consider adding all of them. Weight gives the best improvement. Notice I have a plus sign there. And so on the next round, I'm going to consider adding all the variables with a plus symbol in front of them and removing all the variables with a minus sign, which are already in the model. And so we can see that adding cylinders would give me the best improvements. Now I'm going to go through, I'm going to consider adding all the variables with a plus sign and removing the variables with a minus sign. We see that adding horsepower would give us the best improvements. Now on this step, when I get to here, I see that adding or removing a variable would not change things by the AIC criteria. So I stop, I'm done. Now, something I need to point out, if I did BIC or Maslow's CP or AIC corrected, we could get slightly different models. Typically, they'll be similar to each other, but they will be different. And so here's our final model for stepwise selection. Remember that I can control the range of possible models using that scope argument, which will be a list of a lower and an upper model. Now for model validation, what we're going to do, we're going to use the caret package to work this out for us. So here we can just start by the mean squared error of that model that we built earlier. Miles per gallon depends on cylinders, horsepower, and weight. And you'll notice that I've got a training set and I've got a test set. And so I build my model on the training set, but I check the accuracy. Notice I'm subtracting predictions. I check the accuracy on the test set. And so I could use mean absolute error. Any statistic for model quality could be used at this point. I personally prefer mean square error or using mean absolute error. Now let's do k-fold cross-validation. So for this one, we're going to use the caret package. And what I'm going to do, notice I have this train control parameter in the train function. Inside the train control parameter, I'm going to say that I want to do cross-validation, and I want to do 10-fold cross-validation. And so what this is going to do, this is going to end up subsetting my data into 10 subsets and building a total of 10 models where 1/10 of the data is held out every single time. One thing I like about this approach with a train function from the caret package, it spits out that root mean squared error, the R squared, and the mean absolute error. Now for Bootstrap, it's the same trick as I had before, where what I do in my train control function, I say that method equals boot, and I specify the number of times I'm going to do this. Notice that this is 1,000 times, so there's going to be a lot of repetitions. And very nicely, the train function gives us that root mean squared error, R squared, and our mean absolute error. Now for leave one out cross validation, for my train control, I just say method equals LOOCV, all caps. And then when I run it, it'll once again just spit it out for me, easy peasy, lemon squeezy. All right, so one thing I want to impress upon you is that when I check the statistics of a model, I have to compare model to model on the same data set, same target variable. I could potentially use different predictor variables, but it has to be the same data overall and the same predictor variable. And I'm comparing models to model, and I can't compare mean squared error to mean absolute error. That's an apples and oranges comparison. When it comes to model validation and model quality, it's not so important which method you use. What's more important that you do it. What you make sure you do it in some way, some shape, some form. How you do it, that should be between you and your stakeholders to do what you feel comfortable and what your stakeholders will accept as being correct. All right, well, that's all I got for you. Life is short. Do math.